Hi, welcome back to a video series on MAT 1033 Intermediate Algebra. My name's Sean Perry. This is video number 49 in the series, Polynomial Long Division. So as usual, we want to return to the patterns of numbers and then apply those patterns to polynomials. We're here going to look at the pattern of long division in numbers and why it does what it does. So let's consider now the example of 162 divided by 5. 162 is the dividend, and 5 is the divisor. First, we put the divisor into the division bracket, and we put a 5 out front. We consider how many times we would be able to fit 5 into the first digit 1. The answer to this is 0, and so we leave it blank. We move on and include the next digit, 6, and say, well, then how many times does 5 go into 16? The answer is 3. So we put a 3 up top, and then we multiply the 3 by the 5, and we put that underneath. 3 by 5 is 15. We write that under our 16. Then we say, all right, well, I'm going to take the difference and see how many of those I could get out of this number. Minusing 15, we get 1. Then we drop this next number down, and we continue asking our question about, can we fit 5 into that? So we know that we could fit 5 into 12. We could fit 5 into 12 twice. So we put a 2 above where we are right now, atop the quotient bracket, and multiplying 5 by 2, we get 10. We put that under our 12 and we subtract. And when we take that difference, we get 2. Now we've reached the end. There's nothing else in this bracket. If we wanted to put a decimal place here and do a decimal exercise, we could. But we're working with whole numbers in this section. So 2 is going to be the end result. And notice that 2 is going to be, well, first of all, less than 5, our divisor. But we would write it up top here as the remainder. We'd write R2. And from this, we could write any number of the facts that we learned in the last video. We could write 162 is 32 times 5 plus 2. We could write improper fractions like 162 over 5 as 32 and 2/5. And we should note that the reason this algorithm worked so nicely is because really all we're doing is repeated subtraction. So in the same way that multiplication can be thought of as addition over and over again, you could see subtraction as taking away 5 from 162 a certain number of times until we sort of ran out. We could take 5 away from 162 32 times. But how did this relate to our long division? Well, I mean, the way that it kind of worked is that columns let us keep track of powers of 10. For example, we couldn't take any 5 times 100s away. We had to start with the tens place into 16 tens, or 160. If I take away 30 times 5, I'm taking away 15 tens. I'm taking away 150. And that's precisely how we got our 12. We didn't worry about the last decimal place. We dropped it down. But when we put a 3 up top, we had put a 3 in the tens place. So we were really taking away 30 times 5, even though it only looked like we were taking away 15. Once we did that, we subtracted away 2 times 5 to get rid of the remaining number of 5s we could fit into 12. And that's how we got a remainder of 2. We can't take away any more 5, so that's our remainder. Long division is just a way of keeping track of these powers of 10 and doing this repeated subtraction with columns instead of having to do it one at a time, which would take forever. Now, the main difference between whole number and polynomial division has to do with the requirement that a remainder is strictly smaller, as we noted in the last video. And as we noted in the last video, smaller doesn't mean value, it means degree. We should see why that is. Polynomials can change values. Some values of x might make one polynomial bigger, and other powers of x might flip the inequality entirely. And so we need something better to talk about bigger and smaller for polynomials, and that better idea is degree. This thing has degree 2, this thing has degree 1, and 2 is always bigger than 1, so we consider this polynomial to be sort of more advanced, more complicated, having higher powers involved than this polynomial over here. And instead of the columns, meaning powers of 10, like they did for numbers, tens, hundreds, thousands, and so on, they actually just refer to the different powers of x. And then we can just continue the division algorithm doing this subtraction of polynomials times polynomials until we get a polynomial of smaller degree than the divisor. Once that happens, we're done. Let's flesh this out with an example. Let's say I wanted to do x squared plus 7x plus 13. And I wanted to divide that by x plus 4. We take the dividend, we put it in the quotient bracket, and we put this divisor outside out front. We focus only on the leading terms. I sometimes tell my students, and they don't believe me, that polynomial division is easier, but it's actually true. It's actually easier than the numbers case, because unlike the numbers, where you sort of have to pay attention to the whole number out front here, because you might get, numbers that you have to carry when you multiply, the columns here don't interact that way. So we can focus only on the leading term. It's like we're only ever doing like one-digit division, which is nice. Here I have a leading term of x and a leading term of x squared. And I ask myself, what do I have to multiply by x to get it to be x squared? Well, the answer is I need to multiply it by x. So I put an x up top, and here's a pro tip, put it above the x's, put it in the x's column. Then we multiply. We multiply the x by the term out front. X times x is x squared, and x times 4x is 4x. Now we're going to take a difference, subtracting as before. It'll always cancel your first term. And then minus 4x from 7x gives me 3x. We drop down the next number, and we repeat. Again, only looking at the leading terms. How many times does x go into 3x? Or what do I need to multiply x by to get 3x? And the answer is just 3. So I multiply 3 then by x plus 4. 3 times x plus 4 is 3x plus 12. And then taking the difference, we get 1. We've reached the end. There's no more polynomial left. We're at the end of the quotient bar, and we have this number whose degree is smaller than the degree of the dividing polynomial. That's our remainder. Its degree is 0. It's less than the divisor's degree, which is 1, so we cannot actually go any further. Then we're going to write, well, any number of facts. We could write that this divisor divided by this dividend is this quotient, remainder 1. We could write it in a factored form, or quasi-factored form, where this is a factored part plus a remainder. Or we could write it as sort of an improper rational function with higher degree up top than the bottom, and now a polynomial instead, and a proper rational function, where the degree up top is smaller than the degree in the denominator. Compare this pattern to the mixed number version of fractions. All right, one more example to just kind of take care of a common mistake that gets made frequently, and that has to do with dropping zeros, because in numbers we see them quite clearly, but in polynomials, zero coefficients are often omitted. They're often omitted so we can't see them. Now, but you wouldn't get rid of a zero like this when you did division. If I had 1045, that's so much different than 145. I can't ignore place values. And in the same way, when we have polynomials, I can't ignore zeroed coefficients when I'm doing division. For example, here, notice that I am missing third powers, and I'm missing first powers. So when I write these into the quotient form, what I'm going to need to do is include them as zeros. There are no x's cubed. There are no x's in the dividend. And in the divisor, there are no x's as well. So what I'm going to need to do is leave a 0 there. Include these zeros when you set up your division. Now, we ask the same questions though. How many times would I need to multiply x squared by what in order to get to 3x to the 4th? Well, to get 1 to 3, I need to multiply by 3. To get x squared to x to the 4th, I need to multiply by x. And then multiplying x squared and also minus 1, I get 3x to the 4th minus 3x squared. You could put a 0x here, that's perfectly fine, but you need to keep track of the column. Then when I take that subtraction, I wind up getting minus a minus, which gives me plus 3x squared against 1x squared, that's 4x squared. Now, how many times do I need to multiply x squared to get to 4x squared? I need to multiply it 4 times. So I do that. I get the following two terms, 4x, and then minus 1 times 4 is minus 4. Subtracting cancels the leading term and changes this sign so that I get 2 plus 4, which is 6. And now we've reached the end of the quotient bar. This is remainder 6. As we noted in the last video, just like numbers, if we got 0 for a remainder, this would actually tell us that the divisor was a factor of the dividend. Let's look at an example of that kind. Let's say I wanted to factor the polynomial that I get when I expand x plus 1 squared times x minus 2. So I'll first expand the x plus 1 squared. I'll then expand in this x minus 2, and I wind up with x cubed minus 3x minus 2. Notice that because of this cancellation of the 2x squared term, we don't actually see any x squareds in this polynomial. And if I asked you to factor this, you might be kind of at a loss because, I mean, it's a cubic, but there's not 4 terms. So do I use grouping? What can I do here? It might be a little confusing. We can't do grouping because there's not 4 groups to group. We don't know how to exactly split up this 3x. But let's say we looked at the graph of this thing and we knew from the graph that 2 was a 0. And so x minus 2 was a factor. Well, then we could try dividing by x minus 2. Notice we still need that 0 to represent our x squared, but then I start looking at leading terms and asking the question, what do I need to multiply x by to get x cubed? I need to multiply by x squared. So I multiply this one, I multiply that one, and I wind up with x cubed minus 2x squared. We're subtracting it, which changes the sign, and that gives us 2x squared minus 3x once I drop this down. How many times, what do I need to multiply by to get 2x squared? From x, I need to multiply x by 2x to get 2x squared. So I multiply that, and then I multiply 2x by minus 2 to give me minus 4x. Subtracting changes the sign, cancels this leading term, and negative 3x plus 4x is just positive x. And finally, we say, well, how many times do I have to multiply x to get x? Well, just by 1. So if we multiply this by 1, we get x minus 2. And notice when I take that final difference, I get 0. This means that x minus 2 is a factor, and now we know that x squared plus 2x plus 1 was another factor. And from here, we could factor this quadratic as we know how to do. We already know how to factor quadratics that look like this, so we could just take it home from here. All right, here is your praxis exercises for the day. I want you to look at these 3 rational polynomial functions. We have x cubed plus x plus 1 over x squared plus x. We have x to the 4th plus 2x to the 3rd plus 3x squared plus 4x plus 5 divided by x plus 1. And finally, we have this guy, x squared divided by x squared plus 1. I want you to pause the video at this time and use that division algorithm we just learned to try to write these in the form quotient plus remainder over divisor. Okay, let's see how you did. The first one, I put it in the box. I need this 0 coefficient to hold place. But then I asked myself, x squared and x to the 3rd. How many times do I have to multiply x squared to get x to the 3rd? I have to multiply it by an x to bring that exponent up by 1. X times x squared is x to the 3rd. X times x is x squared. I take this difference and I wind up with minus x squared. Drop down the next term and continue the process. What do I have to multiply x squared by to give me negative x squared? I need to multiply it by negative 1. So I do that, I multiply that by x as well to get negative x, and we take a difference. This gives me 2x plus 1, but look, 2x plus 1, it's not a number yet, but it's smaller in degree than the divisor. So I can't multiply by some polynomial term here to get x squared to be 2x. If I multiply a polynomial by another polynomial, the degree either increases or it stays the same. So we can't multiply by some polynomial and have x squared turn into a 2x. So that means that 2x plus 1 is going to be our remainder. And so we could write this quotient this way, as a division problem is equal to the quotient polynomial plus the remainder over the original divisor. Okay, here's the setup on the next one. I put the dividend in the bracket, I put the divisor up front, and I say, what do I have to multiply x by to get x to the 4th? X to the 3rd. I do that, and I multiply both terms, and I take a difference. Drop the next number down, and we're just going to rinse, wash, repeat this. X goes into x to the 3rd, x squared times, you multiply this out, you take a difference, you drop the next number down, x goes into 2x squared, 2x times, you multiply this over, you bring this down, you take a difference, and continuing on in this way, we are going to need a 2 to multiply by x to give me 2x, and taking this difference, we get 3. So at long last, I get this cubic polynomial, remainder 3. This means we could have taken the original quartic polynomial divided by this linear term and written it as this cubic polynomial plus 3 over the original divisor. Last one, so we had a lot of zeros in this one. There were no x's and no constants. When I divided by x squared plus 1, what I wind up with then is just, well, 1. 1 times x squared is x squared. And if I do this and take a difference, what I wind up with is negative 1. And this is our remainder. And what this tells us is that we could rewrite this quotient as 1 minus this other term, 1 over x squared plus 1. If you want to check that this is the case, try getting like bases by multiplying this by x squared plus 1 over x squared plus 1 and combining. And what you'll see is that the ones would cancel and only x squared would remain. So yes, this really does work. All right, that's going to be it for this particular video. Thank you very much for your patience and have a great day. Good luck with your studies. I'll see you in the next one.